The universe we call home might actually be a cosmic mistake, something that shouldn't exist based on the rules of mathematics and logic we thought explained everything. Beneath its vast, beautiful surface lie contradictions so perplexing that they threaten to unravel our understanding of reality itself. As we dive into these mind-bending illusions, you'll discover why some of the most fundamental truths about our universe might be nothing more than mathematical anomalies, fault lines in the very fabric of existence. This is a journey into the chaos behind the cosmos, where reality bends and the universe's own logic seems to betray itself. The foundations of mathematical reality. Mathematics forms the backbone of our understanding of reality, providing the language to describe everything from subatomic particles to cosmic structures. Yet, the universe's mathematical foundations rest on some surprisingly fragile and occasionally contradictory principles. For example, Euclidean geometry assumes parallel lines never meet, but non-Euclidean geometries demonstrate that this isn't always the case, especially in curved spacetime around massive objects like black holes. These geometries challenge the idea that all of reality can be described by a single, consistent set of axioms. Instead, the universe seems to adapt and expand its mathematical description based on the context, exposing an underlying flexibility or even contradictions that make mathematicians question whether the universe adheres strictly to a conventional mathematical framework. This question deepens when we consider the concept of infinity, central to many mathematical theories, yet problematic in physical reality. Classical mathematics comfortably codifies infinite sets, such as the set of all natural numbers, but physics suggests that spacetime might be discrete at the smallest scales, causing apparent contradictions. For instance, quantum gravity theories propose a Planck-scale structure of spacetime that would prevent the division into infinitely small parts, undermining the assumption of continuous space. Such ideas lead to paradoxes where the mathematical concept of infinity clashes with the physical impossibility of actual infinities, raising questions about whether our mathematical models are mere approximations of a fundamentally finite universe or if they conceal deeper contradictions. Further complicating the relationship between math and reality are unresolved paradoxes rooted in the foundations of set theory, especially those involving self-reference and contradiction. The famous paradoxes, such as Russell's paradox, reveal inconsistencies embedded in naive set theory, which at first glance seems like a fundamental building block of mathematics. Modern set theory tries to avoid these issues through axiomatic systems like ZFC, Zermelo-Fraenkel set theory with the axiom of choice, but even these systems face challenges, especially when extended to larger frameworks like large cardinal axioms. These paradoxes hint at limitations in our pursuit of a fully consistent mathematical description of an infinitely complex universe. They suggest that, at least at the deepest levels, the universe may embody contradictions or paradoxes that prevent a single, all-encompassing mathematical foundation, or perhaps that it requires an entirely different kind of logical framework altogether. The idea that our universe might be inherently inconsistent at its core isn't just a philosophical musing, but a reflection of ongoing scientific and mathematical discoveries. As researchers probe the universe's fabric, from quantum phenomena to cosmic expansion, they continuously encounter phenomena that strain the limits of classical logic and established mathematics. The notion that the universe shouldn't exist within conventional math, yet does, exposes the possibility that reality may operate on principles that are fundamentally non-logical or nonlinear. This deep tension between mathematical rigor and the universe's apparent contradictions invites questions about whether the foundations of mathematics are suited for describing the cosmos, or if they merely serve as intellectual scaffolding that eventually breaks down at extreme scales or conditions. Unveiling contradictions in physical laws. In the realm of physics, the laws that govern our universe appear well established, yet numerous anomalies and contradictions challenge our understanding of reality. Quantum mechanics and general relativity, the two pillars of modern physics, often seem at odds with each other. For instance, quantum theory predicts phenomena like entanglement where particles seem instantaneously connected over vast distances, defying classical notions of locality and speed limits set by the speed of light. Meanwhile, Einstein's equations of general relativity describe gravity's geometric nature, yet struggle to reconcile with the probabilistic, non-deterministic framework of quantum mechanics. This dichotomy raises fundamental questions about the fabric of space-time and the true nature of physical laws. Delving into cosmology, one encounters perplexing contradictions that hint at a universe far stranger than it appears. Dark matter and dark energy, which compose about 95% of the universe's mass energy content, defy direct detection and challenge existing theories. Their existence is inferred solely through gravitational effects and cosmic expansion observations, yet no concrete particle or force has been definitively identified as their source. This incongruity suggests that our current understanding of physics might be incomplete or even fundamentally flawed in describing the universe's most immense scales. These gaps inherently imply contradictions within the framework that has been thought to be comprehensive. On a more localized, yet equally perplexing, level, certain phenomena defy classic physical laws. The concept of perpetual motion machines, which violate thermodynamic principles, still captivates inventors and theorists alike, illustrating how apparent contradictions persist even in engineering. Similarly, anomalies like the Casimir effect, where quantum fluctuations produce measurable forces, reveal that empty space is far from empty. Yet this reality clashes with the intuitive notion of a void. These discrepancies demonstrate that our classical intuition often falls apart when tested against the subtleties of quantum phenomena and high-precision experiments, exposing cracks in the edifice of established theory. Ultimately, these contradictions underscore how our universe might be more complex than our current models suggest. They are not mere anomalies to be dismissed, but are signals that there is much more to discover about the underlying principles governing reality. Each inconsistency opens doors to new lines of inquiry, pushing scientists to explore beyond the well-trodden paths of conventional physics. Unveiling these contradictions not only highlights the limitations of what we know, but also points toward a future where a deeper, perhaps more unified, theory of everything could eventually emerge, one that resolves the paradoxes that currently shape our understanding of the cosmos. Paradoxes of infinity and multiverse theories. In the realm of cosmology and theoretical physics, the concepts of infinity and multiverses challenge our understanding of reality in profound ways. At the core, the notion of an infinitely large universe, or even multiple universes, forces us to confront mathematical paradoxes that seem to defy logical coherence. Infinity, while a useful mathematical abstraction, introduces paradoxes that suggest our universe might not be as straightforward as it appears. For instance, the famous Banach-Tarski paradox demonstrates that, within the realm of pure mathematics, a sphere can be divided into a finite number of non-measurable pieces and reassembled into two identical spheres, something seemingly impossible in the physical world but mathematically consistent in certain contexts. Such paradoxes expose the strange, counterintuitive nature of infinity as a concept, raising questions about whether an infinite universe is genuinely possible or merely a mathematical artifact. Similarly, the multiverse hypothesis amplifies these paradoxes, pushing the boundaries of logical consistency. If an infinite multiverse exists, an idea supported by certain interpretations of quantum mechanics and cosmological inflation, the total set of all possible universes could contain infinitely many variations with all conceivable physical laws. This leads to challenging questions about probability, measure, and typicality. For example, how can we assign meaningful probabilities to events when there are infinite copies of every possible scenario? The so-called measure problem in cosmology refers to the difficulty of defining a proper probability measure over an infinite set of universes. Without a consistent way to do so, predictions become ambiguous. Some argue that such infinities lead to infinite duplicate worlds where every variation of our lives appears somewhere, raising paradoxes akin to the infinite monkey theorem, but on a cosmic scale. Mathematically, these issues extend into the realm of set theory, where certain assumed axioms lead to contradictions when applied to infinite constructs. For instance, the continuum hypothesis, concerned with the possible sizes of infinite sets, remains undecidable within standard set theory, hinting that the nature of infinity itself might be fundamentally ill-defined or incomplete. When these abstract mathematical issues interface with physical theories about the universe, they produce discomforting questions. Could our universe be just one of countless others, each with different rules? Do these infinities imply that the universe is somehow less real, or simply a shadow of a higher, more complex mathematical structure? Such paradoxes show that, while the mathematics describing infinity and the multiverse are internally consistent, they often lead to contradictions or counterintuitive conclusions when applied to the actual universe. That tension underscores just how much of our understanding is still rooted in provisional models, waiting for a deeper theory that can reconcile these contradictions without resorting to infinities that threaten to unravel our logical fabric. Implications for our understanding of existence. The idea that there are mathematical contradictions within the fabric of our universe challenges deeply held assumptions about reality's coherence. Physics relies heavily on mathematics to describe everything from the motion of planets to the behavior of subatomic particles. When paradoxes or contradictions crop up, such as infinities arising where they shouldn't or bizarre solutions that defy logical consistency, they force scientists and philosophers to reconsider what existence actually entails. For instance, certain interpretations of quantum mechanics suggest scenarios that seem to violate classical notions of causality, implying that the universe's underlying logic might be more convoluted and less straightforward than conventional models suggest. These apparent contradictions compel us to think about the universe as a potentially incomplete or provisional construct. If the foundational equations describing reality contain logical inconsistencies, then our understanding of existence might be inherently limited or conditional. It pushes the boundaries of what it means for something to truly exist. If some configurations or states are mathematically contradictory, do they truly exist in any meaningful sense? This problem becomes especially acute in theories like string theory or multiverse hypotheses, where different universes might clash or produce incompatible rules. The presence of these contradictions hints that reality could be more like a patchwork, sometimes consistent, sometimes riddled with paradoxes, challenging the notion that our universe is a perfectly logical entity. The implications ripple outward into our philosophical worldview. If contradictions are part of the universe's fundamental structure, then the search for a theory of everything, a single framework that perfectly explains all phenomena, may be doomed, or at least far more complex than anticipated. Instead of a neat, closed system, we might be looking at a universe that is inherently open-ended, with parts of it forever brushing against boundaries of logical coherence. This can lead to humility in scientific pursuits, but also open new doors for conceptual innovation, pushing us to develop new kinds of logic or acceptance of paradoxical truths. Our entire framework for understanding what it means to exist may need a shift, one that accommodates the possibility that contradictions are embedded within the universe's very fabric, rather than anomalies to be eliminated or ignored. Usnovnoy, Rusgil 5. In the realm of theoretical physics, certain phenomena challenge the very fabric of our understanding of reality, suggesting the possibility of worlds or conditions that seem logically inconsistent, yet might have an underpinning in the mathematical fabric of the universe. This paradoxical notion is exemplified by theories that propose the existence of regions where the laws of physics, as we know them, break down or behave in ways that defy conventional logic. For example, some solutions to Einstein's equations of general relativity hint at the existence of closed time-like curves, CTCs, or wormholes that could, in theory, permit journeys through time or across different parts of the universe without regard to causality. These scenarios suggest worlds that should not exist within the standard framework, but could emerge from the complex interplay of space-time and matter. Mathematical inconsistencies themselves arise from attempts to unify quantum mechanics with gravity. When physicists explore models like string theory or loop quantum gravity, they often encounter contradictions, parts of the equations that cannot be simultaneously satisfied. These contradictions could imply that our current models are incomplete, hinting at realms where logic, as we understand it, collapses under the weight of conflicting equations. For example, in certain interpretations of quantum field theory, Particles can exhibit behaviors, such as tunneling or superposition, that appear impossible within classical confines, yet are supported by empirical evidence. These quantum oddities hint at a universe that isn't entirely consistent in a classic sense, but persist because our models are approximations of a deeper, more intricate reality. Another intriguing aspect revolves around the idea of a multiverse, an infinite or vast collection of universes that might contain worlds with fundamentally different physical constants or laws. If some of these universes operate under laws that are mathematically inconsistent when viewed from our perspective, then their very existence would strongly suggest a universe filled with contradictions, at least from our limited vantage point. These contradictions might manifest as regions where gravity behaves erratically or where particles violate known conservation laws. The prospect of such worlds pushes the boundaries of what we consider logically possible, forcing us to confront the notion that the universe's structure could encompass entities and conditions that are, by strict logical standards, impossible. The idea of the universe that shouldn't exist is not purely philosophical, but rooted deeply in the mathematics underpinning physical theories. We often find paradoxes that challenge our assumptions, such as the notion of singularities or the information loss paradox in black holes. These paradoxes hint at the possibility of worlds or states governed by inconsistent or incomplete sets of principles that nonetheless somehow persist. It begs the question of whether the universe is a stable, consistent structure or a tapestry woven from threads of contradictions, kept intact by some as yet undiscovered principle or law. Exploring these mathematical anomalies and contradictions continues to be one of the most profound and fascinating pursuits in modern physics, revealing worlds that appear to defy the rules, yet might be integral parts of a universe much stranger and more complex than it appears. So here we are, confronting a universe that seems to defy logic, full of mathematical contradictions that challenge everything we thought we knew about reality. From paradoxes embedded in the fabric of space-time to inconsistent equations lurking in the depths of quantum mechanics, these anomalies remind us that our understanding is still incomplete. Yet, it's precisely these mysteries that push science forward, urging us to look beyond conventional wisdom and search for deeper truths. If this kind of mind-bending journey into the universe's quirks sparks your curiosity, make sure to stick around. We've got more fascinating explorations coming up that will take us even deeper into the unknown. Thanks for watching, and don't forget to like, subscribe, and share your thoughts. Because the universe is vast, strange, and endlessly intriguing, and we're just getting started uncovering its secrets together.